Imagine two workers carrying the same heavy box to the top of a building. Both lift the box to exactly the same height. Both do exactly the same amount of work. But here's a question. Who is more powerful? The worker who takes 1 minute or the worker who takes 5 minutes? Most students immediately say the first one. But why? Today we are going to learn the concept that answers this question. In this video, we will study power, what it is, how it is calculated, its units, horsepower, and the difference between work and power. Then we will move to another very important concept, energy. We will discuss different units of energy, kilowatt hour, calorie, and electron volt. So stay with me till the end because many students confuse work, power, and energy. After this lesson, that confusion will completely disappear. Now let us begin with the concept of power. We already know what work is. Work tells us how much energy is transferred when a force causes displacement. But work alone does not tell us how quickly the work is done. And that brings us to the concept of power. Power is defined as the rate of doing work. In simple words, power tells us how fast or how quickly work is done. Mathematically, power equals to work done upon time taken or P equals to W upon T. This is the fundamental formula of power. From the formula P equals to W upon T, we can see that power depends upon two factors, the amount of work done and the time taken to do that work. So more work done means greater power. Also less time taken means greater power. So power increases when work increases and power also increases when time decreases. Let us understand this with a simple example. Suppose there are two coolies at a bus stand. Both are carrying the same load to the roof of a bus. Coolie A lifts the load in 1 minute and coolie B lifts the same load in 2 minutes. Now think carefully. The load is the same. The height is the same. Therefore, the work done by both coolies is exactly the same. But are they equally powerful? No. Coolie A completes the same work in half the time. Since power is work divided by time, so power of A equals to W upon 1 and power of B equals to W upon 2. Therefore, power of A is twice the power of B. Hence, coolie A is twice as powerful as coolie B. This example clearly shows that power depends not only on the work done but also on how quickly the work is completed. Now let us derive another very important expression for power. Consider a body on which a constant force F acts. Suppose the force moves the body through a distance S in time t. We know that work done equals to force into distance. That is W is equal to F into S. Now power is W upon T. Substituting the value of work done, P is equal to F into S upon T. But we know that distance divided by time is average speed. So S upon T equals to V. Therefore, P equals to F into V. Thus, power equals to force into average speed. This is another very important formula for power. Remember, P equals to F into V, where V represents the average speed of the body. Let us now discuss the units of power. SI unit of power is watt and 1 watt is defined as the power spent when 1 joule of work is done in 1 second. Therefore, 1 watt equals to 1 joule per second. For large values of power, bigger units are used. Kilowatt. 1 kilowatt is 10 to the power 3 watt. 1 megawatt is 10 to the power 6 watt. 1 gigawatt is 10 to the power 9 watts. These units are commonly used in power stations and electricity generations. For very small powers, smaller units are used like milliwatt. 1 milliwatt is 10 to the power minus 3 watt. 1 microwatt is 10 to the power minus 6 watt. The CGS unit of power is erg per second. Since 1 joule equals to 10 to the power 7 ergs, therefore 1 watt equals to 1 joules per second, which is equal to 10 to the power 7 erg per second. This is the relationship between SI and CGS units of power. Another important unit of power is horsepower. Before engines were invented, horses were used to perform mechanical work. The power developed by a horse was used as a reference standard. 1 horsepower is equal to 746 watts or 0.746 kilowatt. Remember this value carefully because it is frequently asked in examinations. Students often confuse work and power. Let us compare them. Work is the amount of energy transferred, whereas power is the rate at which work is done. Work tells us how much, but power tells us how fast. Work is measured in joules and power is measured in watts. So work and power are related, but they are not the same thing. Now let us move to another very important concept, energy. Everything around us requires energy. A moving car, a flying airplane, a running athlete, a glowing bulb, all require energy. Energy is the capacity to do work. In simple words, if a body can do work, it possesses energy. The greater the capacity to do work, the greater the energy possessed by the body. We know that work done represents transfer of energy. Whenever work is done, energy is transferred from one body to another. But what happens if work done is zero? Then no energy transfer takes place. Consider a body moving in a circular path. The centripetal force always acts towards the center. The displacement at any instant is tangential to the circle. Therefore, the force is perpendicular to displacement. Angle between them is 90 degrees. We know W is equal to Fs cos theta. Since cos 90 is 0, so work done is 0. Therefore, no energy is transferred. This is a very important concept. The SI unit of energy is joule. 1 joule equals to 10 to the power 7 ergs. For electrical energy consumption, we use watt hour and kilowatt hour units of energy. The most important relation is 1 kilowatt hour equals to 3.6 into 10 to the power 6 joules. This is a favorite board examination question. Please remember it carefully. Another unit of energy is calorie. It is commonly used in heat measurements and nutrition. The relations are 1 joule equals to 0.24 calorie and 1 calorie equals to 4.18 joules. For atomic and nuclear physics, a very small unit of energy called electron volt is used. An electron volt is the energy gained by an electron when it moves through a potential difference of 1 volt. Although we will study this in greater detail in higher classes, you should know that electron volt is also a unit of energy. Let us finish with one final comparison. Energy is the capacity to do work. Power is the rate of doing work. Energy tells us how much work can be done. Power tells us how quickly the work is done. Energy is measured in joules. Power is measured in watts. A machine may have a large amount of energy available, but if it uses that energy slowly, its power may be small. Similarly, a powerful machine uses energy at a faster rate. So today we learned the meaning of power, its formula, factors affecting power, the derivation of P is equal to F into V, SI and CGS units, horsepower, and the difference between work and power. We also started energy, learned its definition, energy transfer, units of energy, kilowatt hour, calorie, electron volt, and difference between energy and power. In the next video, we will solve important numericals on work, energy, and power. If you found this lesson useful, make sure to revise all the formulas and unit conversions because they are extremely important for your ICSE board examination. Thank you for watching, and I will see you in the next lesson.